gonna call this is RN, RN, RN. And I have another voltage here, right? This is my voltage out. This is, let's call this VA, VB, VC, right? There's some voltage out here, right? Right, there's gonna be some voltage across this resistance. The body is just kind of doing circuits. It has 3 sources, right? And those sources are all contributing to this voltage. It's a little bit more complicated than what I've drawn here, but you get the idea, right? It's a coincidence detector, right? Now, if you start thinking about it, these don't have to be, it turns out that these don't have to be the same. And so now the body can start doing different things. It can say, well, this one is going to count double what these are going to count, which I'm going to do by making this resistance smaller. And you can start doing all kinds of calculations, right? This is a very simple calculation, if A, B, and C, right? But you can imagine that there's a lot of synapses coming in, and based on, and you can do all kinds of calculations as a result of it. Does that make sense? I know I've gone over a lot, right? Because I told you I was going to do all of neuroscience, right? And people will spend, a month on these kind of ideas. But I guess my only thing, what I want you to know is that if you understand this, okay, and you understand that you can connect this circuit, right, to these kind of circuits, just via resistance, you can now create something that's doing these different kinds of calculations. And again, I will send you videos that, there's some really nice explanatory videos that unpack this in a lot more detail. So far, so good? Okay. I have to tell you one more, I think, general concept, all right? We talked about a synapse. People will talk often about 2 kinds. They'll talk about an excitatory synapse, and they'll talk about a inhibitory synapse. And I'll explain this, and then I will bring it back to gate control. Remember your uncle and his knee pain that you cured? And then we're done. Okay, and then we're done. It turns out that there's different types of goop that these neurons spit out. And with it, there's different types of receptors associated with them, right? So if I spit out something called glutamate, this cell has to have a glutamate receptor. Okay, it's not going to pick up ice cream or, right, anything else. It's sensitive to that, right? There can be another different cells showing up. Remember, we can have multiple cells showing up, right? This cell may spit out something else. Let's call it GABA. And this cell will only be responsive to it if it has a GABA receptor. Glutamate, when it's released in a synapse, makes it an excitatory synapse. I'll explain why in a sec. If GABA is released, it makes it an inhibitory synapse. How do you make an inhibitory synapse? Like that. Instead of having this be positive, we're going to put the positive here and the negative here. An inhibitory synapse is a synapse that tends to push the membrane potential away from where it wants to go, while an excitatory synapse tends to push it up. So the body has come up with multiple types of synapses, which are distinguished based on the chemical that they release. And sometimes when this connection happens, it pushes the cell closer to firing an action potential, and we will call that an excitatory synapse, right? Certainly the ones that make your muscles contract, right, are excitatory. But there are other situations where this cell fires, it will release a different kind of chemical, and that will actually push the membrane potential down. So now you can see the situation where some of these cells are trying to push the cell up, some cells are trying to push the cell down, and whether it fires or not is now a more complicated kind of processor. Let's bring it back to gate control. We're done. The gate control theory, right, is at the highest level, if you rub it, it will feel better, right? Or if you give your uncle a weak electrical stimulator and tell him to put it over the part that hurts and turn it on until he feels tingling, but no more, right, his pain goes away. What was the model that we generated for that? It says hand pain. Here's your brain, right? This is also where you feel the pain, right? So here you have a pain axon. There's an axon whose job it is to transmit the pain to your brain, but it doesn't go direct. It stops in your spinal cord, where it makes a synapse. It goes here. There is a synapse, and then there is another cell. Let's go draw the line the way the information is flowing here. There is another cell that transmits the information up. It is not a direct line, right? The pain is not going from here to here. There's a synapse along the way, right? This is a excitatory synapse. What that means is that when this one goes, squirt, the next one goes. And then you feel pain. You have other axons here. Let's call them the touch axons. Right? This is not painful. They're just saying, oh, someone's rubbing it, right? Like, you know, right? Your niece hurts her knee or something, you gotta rub the knee, right? These axons also go into the spinal cord, right? But then they go, it's a little bit busy here. All right, we'll label this is pain to brain. This is touch to brain, right? They go in to the spinal cord, but then without making a synapse, they run straight up, right? It's actually more important for your brain to get touch information than pain information. I mean, the difference is milliseconds, but the brain really wants to know about touch, all right? Very quickly, no stops, not this time, straight up we go, all right? And if you remember, these are also, so here's information. These are also bigger axons. They conduct faster to begin with. So that's a straight shot. But there's one more piece of it. This axon here splits. There is a split on the line. All right? How do we model a split? Like this. It's always the same thing, like this. How you model a split? If the split is here like that, that's a split. Okay? You have one here, and then they're going off in right? Different direction. There's nothing conceptually hard about that. It's literally the line is split, and then we have a booster, booster, booster. The boosters are heading in opposite directions, right? Just like here it converged, we can split it, no problem. So this one here is going up to the brain, right? That's why your uncle feels that his knee is tingling. But it also goes down here, right, to the same area, and it also makes a synapse. Except this synapse is inhibitory. Why is it inhibitory? Because it releases a chemical, right? There's two kinds of chemicals, right? Some chemicals are the excitatory kind, and some are the inhibitory kind. And that's the gate. Because this cell here, which job it is to tell the brain that your uncle has knee pain, right, is being excited by the pain axon, but simultaneously it's being inhibited by the touch axon. And the combination of the two cancel out, and therefore it doesn't do anything. So your uncle's brain never got the I'm in pain. It never got it. He's thinking, oh yeah, the pain's gone. Now where did the pain go away? It didn't go away here. We didn't, right? It didn't go away here. The pain went away here, and it never got to his brain. And so the notion of how a TENS device works, right, is very much related to the fact that you have synapses, and it's very much related to the fact that you have excitatory synapses and that you have inhibitory synapses. So now we've come sort of full circle, right? And I can spend the rest of class talking about what we're going to do with stimulation, right? But you could see, you know, we always talk about how you have to have some like understanding, right, of how the brain works in order to do some interfacing. And you can see why I needed to give you this very, very, very basic level of understanding, because clearly we can't understand how TENS works if we don't understand that you have excitatory and inhibitory synapses, and that you have a situation where you have cells that are sort of integrating that information, right? They're making a decision. And in this case, if this is that cell that we just saw, right? If this is the pain, it would normally generate an action potential. But if this is the pain plus the tingling, right? And this is now an inhibitory, oh, they cancel out and it doesn't generate an action potential. Does that make sense? Any questions on that? I know there was a lot, which is what I'm saying. There's a lot of good content online that presents it in a very different way than the way I presented it, but you'll talk more about synapses and integration and conduction, but now you see how it all comes together. And it's important to us. If you want to make devices that make people not be sad or suicidal, right? If you want to make devices that can make paralyzed people walk, you need to have this background of neuroscience, because that is the system that we're interacting with, right? We're going to be going into the system. We're going to be trying to modulate that system. We need to have a sort of understanding of how that system works, or else we're not going to really know how to modulate it. And gate control is the best idea. The idea, TENS didn't come first. The idea came first. And then, right, these guys, Melzak and Wall, said, wait a second, if that's true, then that's why if you rub it, it feels better. And it also means that, wait, if we put electrical stimulation on, which, if anything, should make things worse, it might actually make things better as long as we're activating the tingling part of it. And then they tried it, and it worked. And that led to TENS, right? So the idea came first, then we were able to design an intervention, right? You have the idea, then you go back to your electrical engineering and make a stimulator that makes that idea a reality. Does that make sense? All right. All right, that is it for today. Any more questions? I don't expect all this to be like super simple right now, but your homework will be probably for this Wednesday and for Sunday a bit of watching. Great, right? You can watch in the subway, you can do whatever you want, but I'm going to have you do a little bit of watching for your homework, okay? All right. Any questions about past homework? You can email me. You can come see me. If someone asks, you can see me after class, any class you want. Okay, there's no, it's good. You can